Yeah, this is Ashutosh Singh, Assistant Professor in GIMS Technical Campus, Greater Noida. Today, this is lecture number 5 for heat and mass transfer. In this lecture, heat transfer through a fin and efficiency and effectiveness of the rectangular fin. Elementary step and Qx and Qx plus x, these are the heat transfer rate at a distance x is equal to x and x is equal to x plus dx. So apply the fundamental general heat and we this equation. Let Qx plus dx is equal to heat conducted out of the element along x plus dx. So mathematically Qx plus dx is equal to Qx plus del over del x Qx multiplied by dx. It is denoted by the equation number 2. But Newton's law of cooling or heat transfer through convection is equal to the heat transfer by convection from the surface of the element of the fluid. So mathematically Q convection या Q convected is equal to H multiplied by area of convection multiplied by temperature gradient या temperature difference. So equation number 3 represent the heat transfer through convection, that is Q convection is equal to H multiplied by area multiplied by temperature difference. This is T minus T infinite, where T infinite is equal to exposed to the ambient temperature and T is equal to arbitrary temperature at a distance x. So the next is area of convection is equal to the perimeter of the fin multiplied by length of the fin. So we calculated the area of convection is equal to P multiplied by dx, where dx is equal to the small elementary length of the fin, where T is equal to the temperature of the different elements. So we assume certain assumptions, that assume steady state condition and write the energy balance equation for the element. We apply the energy balance equation. As per this equation, the heat conducted into the element should be equal to the heat conducted out of the element plus heat convected from the element. So this is a basic fundamental heat transfer equation. Mathematically Qx is equal to Qx plus dx plus Q convected, or we can say Qx is equal to Qx plus del over del x multiplied by dx into dx plus H multiplied by area of convection multiplied by T minus T infinite. Putting the values of equation number 1, 2 and 3, we obtained 0 is equal to del over del x minus Ka dt by dx plus Hp dx T minus T infinite. This is a mathematical expression for the heat transfer through a rectangular fin. On solving this mathematical equation, following results, that is del square T over del x square minus Hp divided by KCS multiplied by T minus T infinite is equal to 0. So del square T over del x square is represented a second order differential equation. So put T minus T infinite is equal to theta. Theta is equal to the temperature difference. It is a mathematical segment, or it is a mathematical constant. So theta, so dt by dx is equal to d theta by dx, or we can further differentiate this equation. We get d square t over dx square is equal to d square theta over dx square. Putting the value of d square t over dx square in the fundamental equation, now we obtain d square theta over dx square minus m square theta is equal to 0. We also assumed Hp divided by a KCS is equal to m square. So this equation d square theta over dx square minus m square theta is equal to 0 is known as the fundamental equation for a rectangular fin of second order differential equation. So after integrating this equation, the following equation is obtained. This is theta is equal to C1 e to the power minus mx plus C2 e to the power mx, where C1 comma C2 are the constant, and we get this constant value by applying the boundary condition. So there are three types of boundary condition, so or we can say there are three types of cases. So let's start the first case of rectangular fin. This is the first case where the fin is inserted into a hot surfaces, and another end is subjected to a ambient temperature. So and C1 and C2 are the constant of integration, and that are to be obtained from the boundary condition. So note, for pin fin the values of AC and P will be different. The boundary conditions. So apply the boundary condition at x is equal to 0, or we can say at x is equal to 0 it is the root cause, it is the root of the fin. At x is equal to 0, t is equal to t naught, and theta is equal to theta naught is equal to t naught minus t infinite. The another boundary condition, that is at the tip, depends on the three different cases with as follows. Case number first, the fin is infinitely very long, so we assume the length of the fin tends to infinite. Where the fin is infinitely long, the temperature at the tip of the fin will be essentially that of the fluid. So at x tends to infinite, theta tends to 0. So putting the values of putting these boundary condition first and second in the basic equation, we get C1 is equal to 0 and C2 is equal to e to the power C2 e to the power minus mx. So apply boundary conditions, the final results are obtained. T is equal to t naught minus t infinite multiplied by e to the power minus mx plus t infinite. On further solving, the heat transfer through fin is equal to under root of HPKACS T naught minus T. This is a final expression for calculating the heat transfer rate through a rectangular fin when we assume that the fin tends to infinite. So this is the final expression under root of HPKACS T naught minus T infinite. Case number 2. In case number 2, the fin tip is insulated. We assume the fin tip is insulated. It means Q conduction is equal to 0, Q convection is equal to 0, because this portion is insulated. There is no temperature gradient, so there is no heat loss. Finally, Q conduction and Q convection should be equal to 0. Apply these boundary condition on the fundamental equation. When the fin tip is insulated, then the conduction heat transfer at x is equal to L is to 0, that is minus k dt by dx is equal to 0. Hence the boundary condition will be dt by dx at x is equal to 0, at x is equal to L is equal to 0, and d theta by dx at x is equal to L is equal to 0. So finally, putting the values of C1, C2 in the fundamental equation, we obtained the final results, that is theta upon theta naught is equal to t minus t infinite divided by t naught minus t infinite is equal to cos hyperbolic ml minus x divided by cos hyperbolic ml. So this equation is known as the temperature distribution equation in second case when the tip of the fin is insulated. So putting the values of putting these equation in a Fourier law, we know that the Fourier law, this is Q is equal to minus K multiplied by A multiplied by dt by dx. So if we are calculating the total heat loss from the fin, we assume x is equal to 0. So x is equal to 0 means root base. So on solving this equation, we get the heat loss of the fin, that is Q fin is equal to under root of HPKACS T naught theta naught tan hyperbolic ml. So this is a final expression for calculating the heat transfer rate in case of fin tip is insulated. So there are mostly two cases very important. Case number 1 means the length of the fin tends to infinite, and the case number 2 when tip is insulated. So my next is and fin effectiveness. Fin efficiency and fin effectiveness, these are very important terms related to the fin. So if we talk about the fin efficiency, the efficiency of a fin is defined as the ratio of the actual heat transferred by the fin to the maximum heat transferred by fin if entire fin area were at the base temperature, or it is defined as the ratio of the actual heat transfer rate taking place through the fin at the maximum possible heat transfer rate that could occur through fin when the entire fin is at root temperature or a base temperature. The entire fin will be at its room temperature, when the material of the fin has infinite thermal conductivity. So mathematically the efficiency of the fin is denoted by neta. Neta is equal to Q actual divided by Q maximum possible heat transfer. So mathematically Q actual is equal to under root of HP K ACS T naught minus T infinite, and Q maximum possible is equal to A multiplied by area of fin multiplied by T naught minus T infinite. So finally we get the efficiency of the fin is equal to 1 upon ml, where m is equal to a mathematical constant and L is equal to the length of the fin. So, and second case, when a fin is insulated, at that case the neta insulated tip is equal to Q actual divided by Q maximum possible, and Q actual is equal to under root of HPK CS theta naught T hyperbolic ml divided by H into area of the fin multiplied by T naught minus T infinite, and in that case the efficiency of the fin is equal to the tan hyperbolic ml divided by ml, where area of the fin is equal to convective heat transfer of fin or perimeter of the fin multiplied by length of the fin. So the efficiency of the fin forms a certain criteria for judging the relative merits of fin of different geometric or materials. So the next, of the fin. Effectiveness of the fin is the ratio of the fin heat transfer rate to the heat transfer rate that would exist without a fin, or we can say it is defined as the ratio between the heat transfer rate with fin and without fin. Mathematically, efficiency of effectiveness is denoted by epsilon. Epsilon is equal to, for first case, is equal to Q fin divided by Q without fin. Mathematically, for first case the expression is under root of HP divided by Kp divided by H multiplied by AC, and for second case the effectiveness, that is epsilon insulated tip, is equal to tan hyperbolic ml. So the fin effectiveness should be greater than unity if the the heat transfer from the primary surface is to be improved. So it has been observed that use of fin on surface is justified only if when Pk divided by HAS should be always greater than 5. It is very important point. And the second important point is, if the ratio of the perimeter and the cross section is increased, the effectiveness of fin is improved. Due to this reason, thin and closely spaced fin are generally preferred, or the lower limit on the distance between two adjacent fin is governed by the thickness of boundary layer that develops on the surface of the fin. Though the next is, the use of the fin is only justified where the heat transfer coefficient H is small, or we can say if the value of H is very large, then then the fin may actually produce a reduction in heat transfer rate. And the last important point is, if it is also apart from the apparent that the use of the fin will be more effective with material of large thermal conductivity, although copper is superior to aluminium regarding thermal conductivity, yet fin are generally made of aluminium because it is cheaper in cost and lighter in weight. So these are the basic important points regarding fin effectiveness. So if the effectiveness is equal to 0, or we can say fin does not affect the heat transfer at all, and if the effectiveness is less than 1, fin acts as insulation if thermal conductivity K of the fin is high. And the third point is, if the effectiveness is greater than 1, heat transfer will be increased. So effectiveness and efficiency, these are two very important terms which is related to the fin heat transfer. So thank you.